Protons and neutrons make up a nucleus, which is the foundation of nuclear science. Nuclear binding energy is the energy required to keep the protons and neutrons of a nucleus tightly packed together. Fusion and fission involves the disintegration or binding of elemental nuclei and isotopes. The difference in mass before and after the reaction can be acknowledged to the nuclear binding energy. Basically, nuclear binding energy is considered as mass. To calculate the energy released during mass destruction in both nuclear fission and fusion reactions, we use Einstein's equation that equates energy and mass, which is E equals mc squared. There are two types of nuclear reactions, fusion and fission. Fission is the splitting of a nucleus that releases free neutrons and lighter nuclei as the number of protons are changing in the nucleus. Particles such as neutrons, photons, and alpha particles are also released from the reaction. The fission of heavy elements is highly exothermic. The unique feature of nuclear fission reactions is that they can be contained and used in chain reactions. The chain reaction is the foundation of nuclear power. One of the well-known elements used in nuclear fission is uranium-235. When uranium-235 is bombarded with a neutron, the atom turns into uranium-236, which is even more unstable, resulting in the nucleus splitting into daughter nuclei such as krypton-92 and barium-141 and free neutrons. The byproducts of a fission reaction are highly radioactive, as the unstable uranium-236 also releases gamma radiation and therefore difficult for waste storage. Contrariwise to nuclear fission reaction, nuclear fusion reaction is the process of joining two nuclei to form a heavier nucleus. Moreover, fusion of a nuclei with lower mass than iron releases energy, while fusion of nuclei heavier than iron generally absorbs energy. This trend is known as the iron peak. In addition, extreme conditions must be met in order for the reaction to take place. The elements must be in a really dense environment and the atoms must be moving at very high speeds. Also, extreme high temperatures up to 15 million degrees Celsius must be reached to force the nuclei together. It takes so much heat to achieve a nuclear fusion reaction even for light elements such as hydrogen is because in order to overcome the electrostatic repulsion by the protons of both the hydrogen atoms, both of the hydrogen nuclei need to accelerate at super high speeds and get close enough in order for the nuclear force to start fusion. The result of nuclear fusion releases more energy than it takes to start the fusion, so delta H of the system is negative, which means the reaction is exothermic. The reaction therefore releases the energy in the form of heat and radiation. The power of the energy in a fusion reaction can be observed in the natural world, as fusion is what drives the energy that is released from the sun and a lot of the stars in the universe.
Created using Powtoon.